So in this video, let us discuss about the quality factor. So we already discussed about the LCR circuit. LCRs, which means a circuit in which the inductor, capacitor and resistor are connected in series. And in that circuit, if we plot the angular frequency, if we take the angular frequency in the x-axis and current in the y-axis, we will get a graph like this, somewhat like this. And clearly this is the peak value of the current, and that happens, this is the peak value of current, and that happens when the frequency is at the resonance. We call that omega r. That is when the at resonant frequency the current in the LCR circuit is maximum. Now, how will we find the quality factor? For that, here the current is I0, and we know the expression for the impedance, that is impedance in the LCR circuit, Z is equal to, we know it's R square plus XL minus XC whole square. But we know when omega is equal to omega r, that means when the frequency is at, when it is at resonant frequency, we have the inductive reactance equal to capacitive reactance. And at that point, this becomes 0 because XL equal to XC means XL minus XC equal to 0. So Z is equal to root of R square, which means R. That is, Z is equal to R when omega is equal to omega r. Clear? So keep this in your mind, which also implies that the impedance of the circuit is equal to the resistance of the LCR circuit at resonant frequency. Clear? Now, I took another frequency, let's say another frequency omega 1 and omega 2. These are two different frequencies which are at equidistant from the omega r. That is, this length, I can call that as delta omega, and this length remains the same, delta omega itself. That is, this omega 1 and omega 2 are equidistant from omega r. Clear? Since this graph is symmetric, both these values omega 1 and omega 2 gives the same current. Let's write it as I dash. Also, this omega 1 and omega 2 should be taken in such a way that the current in the LCR circuit must be 1 by root 2 times the peak value of current. That is 1 by root 2 times the peak current. I took omega 1 and omega 2 in such a way that the current must be 1 by root 2 times the peak current. Clear? That is, I dash is equal to I0 divided by root 2. We know at omega equal to omega r, the maximum current will be V0 times the impedance Z. But we know V0 by impedance is actually R when omega equal to omega r. So I can put the value I0 equal to V0 by R in here. So it will be V0 by R divided by root 2. So which is equal to V0 divided by root 2R. So whatever comes to the denominator, that is voltage by this value will be the impedance. So when omega equal to omega 1 and omega is equal to omega 2, we have the impedance Z equal to root 2 times R. Clear? Here the impedance is Z. Here at this point we have Z is equal to, let me write like this. At this point Z is equal to R, and here the impedance Z is equal to root 2R. Clear? Also we have omega 1 is equal to, this omega 1 is equal to omega R minus delta omega. See, this omega R minus delta omega gives omega 1. See, this whole length is omega R and this length is delta omega. So omega 1 will be omega R minus delta omega. Also omega 2 is actually omega R. Up to this length it is omega R, then you should add this delta omega. Clear? So plus delta omega. Now if you find the difference of omega 2 and omega 1, you will get omega R plus delta omega minus omega R minus delta omega. Therefore, omega 2 minus omega 1 will be, omega 2 minus omega 1 will be, this will become omega R plus delta omega minus del omega R plus delta omega. Minus and minus will become plus. You can cancel this. So it will be omega 2 minus omega 1 is equal to 2 times delta omega. And we call this difference as bandwidth. Clear? Now quality factor is actually, you can represent quality factor as Q hyphen factor, that is quality factor, is the ratio of the resonant frequency, that is this frequency, to the bandwidth, that is 2 delta omega. So this is the expression for the quality factor. But we must find the quality factor in terms of resistance, inductance and capacitance. Okay. For that, let's take the expression for the impedance. We know Z is equal to, in an LCR circuit, Z equal to R square plus XL minus XC whole square. Again, you can write XL is equal to omega L, where omega is the angular frequency, L is the inductance. XC is equal to 1 by omega C, where C is the capacitance. So Z is equal to root of R square plus omega L minus 1 by omega C whole square. Clear? Now we have at this value of current, that is at I dash, we have at that current, angular frequency is omega 1 and omega 2, that is at omega is equal to omega 1 and omega is equal to omega 2. We have Z is equal to, I already written that, but for this derivation I will write it again, Z equal to root 2R. So this will become root of R square plus omega L minus 1 by omega C whole square is actually Z is equal to root 2R. Now let's call this as equation number 2. Now squaring both sides, you always keep this in mind, quality factor equal to omega R by 2 delta omega or bandwidth. Now squaring both sides, we can remove this root on the left side. So it will be r square plus omega L minus 1 by omega c whole square is equal to, this will become root 2r whole square. So this is equal to r square plus omega L minus 1 by omega c whole square is equal to 2r square. Taking this r square to the right, you will get omega L minus 1 by omega c whole square will be 2r square minus r square, which will give r square. Clear? Now taking the square root on both sides, that is, we have omega L minus omega c is equal to plus or minus root of r square, which will give plus or minus r. Clear? That means we have omega L minus 1 by omega c equal to plus or minus r. So we have two values of omega, that this happens at omega equal to omega 1 and omega equal to omega 2. So when omega equal to omega 1, I can put these two values in this equation. This will become omega 1. So omega 1 L minus, because this satisfies, these two variables satisfies this equation, because it is the solution. So omega L by 1 by omega 1 c is equal to, let's take the first value, minus r. Let's call that as equation number 3. Now when omega is equal to omega 2, you can write omega 2L minus 1 by omega 2C is equal to R. That's our equation number 4. Now, if you take the difference of equation 4 and 3, that is when I subtract 4 from 3, sorry, 3 from 4, you will get, this will be omega 2L minus 1 by omega 2C minus omega 1L minus 1 by omega 1C equal to R minus minus R. Clear? I am subtracting 3 from 4. So R minus minus R. So this can be simplified as omega 2L, taking these two terms together, omega 1L minus 1 by omega 2C, minus and minus will become plus. So 1 by plus 1 by omega 1C equal to R plus R. So this can be rearranged, or you can take the omega L as common, omega 2 minus omega 1 times L plus, let's first write this one, 1 by omega 1C minus 1 by omega 2C is equal to R plus R is 2R. So omega 2 minus omega 1 L plus 1 by C, you can take that as common, times 1 by omega 1 minus 1 by omega 2 is equal to 2R. So this is equal to omega 2 minus omega 1 L plus 1 by C. You can cross multiply this one. So it will be omega 2 minus omega 1 by omega 1 omega 2 equal to 2r. Clear? Now in both these terms, omega 2 minus omega 1 is common. So you can take that out. So omega 2 minus omega 1. Now there is a L left in here, L plus 1 by, this one is taken out. So only 1 by C omega 1 omega 2 remains, is equal to 2r. Clear? Also we have we already know omega 2 minus omega 1 is equal to 2 delta omega. That is the bandwidth. And we know omega 1 into omega 2 is actually, omega 1 we took that as omega r minus delta omega. And omega 2 is actually omega r plus delta omega. We have written that before. This omega 1 equal to omega r minus delta omega and omega 2 equal to omega r plus delta omega. This is of the form a minus b into a plus b. So that will give omega r square minus delta omega square. That is omega 1 into omega 2 is equal to omega r square. See, delta omega is very small. So delta omega square, you can approximate that to 0. So omega 1 into omega 2 equal to omega r square. And in the LCR circuit, we already derived this expression. Omega r is actually 1 by root LC, where L is the inductance and C is the capacitance. So omega 1 omega 2 will be 1 by root of LC square, which is equal to 1 by LC. Clear? Now let's plug in these two values in this equation. So in this equation, so omega 2 minus omega 1 is 2 delta omega into L plus 1, this can be written as 1 by C into 1 by omega 1 omega 2 equal to 2r. You can cancel this 2 and this 2. So delta omega into L plus 1 by C into C, omega 1 omega 2 is 1 by LC. So 1 by LC equal to R. You can cancel this C and this L moves upward. So the expression will be delta omega into L plus, this L moves to the numerator, so there is L equal to R. So delta omega into 2L is actually R, or you can write 2 delta omega is equal to R by L. Clear? So bandwidth is equal to R by L. Now let's take the expression of quality factor. We know Q factor is equal to the ratio of resonant frequency by the bandwidth. So resonant frequency is actually 1 by root LC divided by 2 delta omega is R by L. This can be written as 1 by root of LC into this L moves to the numerator L by R. So this is equal to 1 by, this is root L into root C into L can be written as root L into root L. Root L into root L is L by R. Cancel this L. So the final expression will be 1 by R root L by root C. So the quality factor Q factor is equal to 1 by R. This can be written as root L by C. So this is the expression for the quality factor. So from the equation itself, you know, when R is less, Q is high, quality factor is high. So quality factor is sharp. We can say that quality factor is high means the resonance is sharp. So when the resistance of the circuit is less, that circuit gives high quality factor. Clear? And the quality factor increases with the L. With L increase in inductance, the quality factor increases, but with decrease in capacitor, quality factor increases. Clear?